friend, welcome to this lecture. In this lecture we will continue our study of phase portrait. So, in previous lectures we have discussed what do you mean by phase portrait, and we have discussed the different type of critical points. So, in this lecture we will discuss more about phase portrait. In fact, we will focus on linear system of dimension 2, so that we can portrait the phase portrait on your xy plane, and we also try to see that the critical point of the linear system is of what type. So, for that let us consider the following linear differential equation. So, consider the linear system dx by dt equal to ax plus by and dy by dt equal to cx plus dy, where a, b, c, d are a real constant, and here we can say that this system has 0, 0 as an equilibrium point, and if we impose one more condition that determinant of a, b, c, d is non-zero, then 0, 0 is the only critical point of this system 1 here. Now, let us find out the solution of 1 here. So, for that you simply assume that x equal to a e to power lambda t and y equal to b e to power lambda t be two possible solution of this, and then try to find out the solution of this. In fact, if you look at here, if I simply denote this x y as a vector, then it is nothing but your a, b, c, d and x y, it is written here. So, it is a system like this, and your solution which we are assuming is the following, that x y is equal to e to power lambda t and this a and b here. So, here we need to find out this vector a b and vector a b and the constant lambda, such that it will work as a solution here. So, that is why we have writing that x equal to a to e to power lambda t and y equal to b e to power lambda t be the possible form of the solution, and we need to find out the condition for the values of a, b and the lambda. So, so here we have already seen that this lambda is the characteristic root of the matrix A, and AB is the corresponding eigen vector for that eigenvalue lambda here. So, for that look at here, then for 2 to be a solution of 1, lambda must satisfy this equation, that is lambda square minus a plus d lambda plus ad minus bc equal to 0, which is nothing but the characteristic equation of A in terms of lambda here. So, here we call this equation number 3 as the characteristic equation of 1, and since it is a quadratic equation, then there is a possibility of having two roots, lambda 1 and lambda 2. So, let lambda 1 and lambda 2 be the roots of the characteristic equation 3, and we claim that the nature of the fixed point, that is 0, 0 depend upon the nature of the roots of lambda 1 and lambda 2. So, here we already know that 0, 0 is a critical point, or say equilibrium point or stationary point or fixed point, and the type of the critical point, whether it is say node or say a stable node, unstable node, focus, spiral, it will all depend on the behavior of lambda 1 and lambda 2. So, based on the root lambda 1 and lambda 2, we have following 5 cases, and we will consider each and every case, and based on each case, based on the conditions given in each case, we try to find out the behavior of 0, 0, whether 0, 0 is what kind of critical point. So, first case based on lambda 1 and lambda 2 is that both lambda 1 and lambda 2 are real, unequal and of the same sign. So, it means that here lambda 1 is not equal to lambda 2, and but the sign is same, whether it means that whether both may be positive or both may be negative. And the second case is real, unequal, but in this case they are having opposite sign. So, it means lambda 1 is not equal to lambda 2, and it may happen that lambda 1 is positive, but lambda 2 is negative, and it may be the otherwise also. So, this is the case 1 and 2. Here lambda 1 is not equal to lambda 2. One is that they are having the same sign, and the other case is they are having the opposite sign. Now, third case that they are real and equal. So, it means that the first two case is corresponding to unequal roots and the third case is corresponding to equal. So, 1, 2, 3 they are all real, lambda 1 and lambda 2 both are all real, and it may be unequal or equal. And the fourth case and fifth case are corresponding to the case when lambda 1 and lambda 2 are complex. So, they are not real. So, again in complex we have two sub cases, that is conjugate complex but not purely imaginary. So, it means that they are having both real part as well as the imaginary part, and fifth case is corresponding to purely imaginary part. So, it means that a real part is missing here. So, these are the 5 cases, and based on each case we have one theorem and which tells us that in under this condition the behavior of 0, 0 is what. So, let us consider the first theorem which correspond to the case 1. So, here the theorem says that the roots lambda 1 and lambda 2 of the characteristic equation 3 are real, unequal and of the same sign, right. Then the critical point 0, 0 of the linear system 1 is a node. So, so here the case 1 which is for lambda 1 and lambda 2 both are real, unequal and of the same sign, then the critical point 0, 0 is a node. Now, whether it is a stable node or unstable node, that will depend on the sign of lambda 1 and lambda 2. So, first let us assume that lambda 1 and lambda 2 are both negative, and let us assume this, that lambda 1 is less than lambda 2 is less than 0. Since they are real or unequal, so we can take this condition lambda 1 less than lambda 2 less than 0. So, here we just for simplicity we are assuming that lambda 1 is less than lambda 2 and greater than 0. So, it may be otherwise also. Now, in this case your solution of 1 may be written as x equal to C1 u1 e to power lambda 1 t plus C2 v1 e to power lambda 2 t, and y as C1 u2 e to power lambda 1 t plus C2 v2 e to power lambda 2 t. In fact, in this case when your dimension is 2 and we have two distinct eigen values, then we have two distinct eigenvectors. This we have already done. So, let us call this as v and u are two eigenvectors. So, u is given as u1 and u2, and v I am writing as v1 and v2 here. So, let me write down the solution here. The solution xy is given as C1 e to power lambda 1 t. Now, corresponding to e to power lambda 1 we have eigenvector say u1 u2 plus C2 e to power lambda 2 t, and corresponding to lambda 2 we have v1 and v2 here. So, when you simplify you will get what, x equal to C1 e to power lambda 1 t u1 plus C2 e to power lambda 2 v1. Similarly, y I can write it C1 e to power lambda 1 t u2 plus C2 v2 e to power lambda 2 t here. So, the solution form of the solution is given from this. Okay, so here this u1, u2, v1, v2 are some constant, and here we are assuming that u1, v2 is not equal to v1, u2. So, that is very obvious from here, because here v1, v and u are linearly independent to each other. So, it means that I cannot write v as some constant multiple of u here. So, it means that so v cannot be written as constant multiple of u, means let us take v1, v2 as say k times say u1 and u2, and you can say that this condition is easily verified here. And now here since C1 and C2 are some arbitrary constant, and we can write down the general solution as xy here. Here now we consider different cases corresponding to this C1 and C2. So, now let us assume that C2 is equal to 0. So, when C2 is equal to 0, then we have the solution x equal to C1 u1 e to power lambda 1 t, y as C2 u2 e to power lambda 1 t, or I can say that it is nothing but xy equal to say C1 and here we have u1 and u2 and e to the power lambda 1 t here, right. So, now similarly choosing C1 equal to 0, here we have assumed C2 equal to 0. So, we have solution like this, and if we assume that C1 is equal to 0, then your solution will be xy equal to C2, here we have V1 and V2 e to the power lambda 2 t, right. Now, so now once we have this is corresponding to C1 equal to 0 and the earlier one is corresponding to C2 equal to 0. Now, here when consider this case when C2 is equal to 0, but C1 is non-zero, then C1 may be positive and C2 may be negative here. So, here if we consider that C1 is positive, then this u1 and u2 simply represent a vector here, and we can write here that let us consider this. So, u1 u2 represent a point here somewhere, right. So, now this C1 u1 u2 e to the power lambda 1 t is basically this is your u1 u2. Now, C1 is just a scaling factor and e to the power lambda 1 t is some scaling factor. So, it will give you some point on this line. So, it means that this will represent a line passing through the point u1 and u2 here, right, and it is passing through this. Similarly, if you look at this may represent, suppose V1 V2 is somewhere here, V1 and comma V2 here, then this line represent the vector V1 and V2, and if C2 is positive, then it will represent the line like this, and the earlier one line is like this. Now, if C1 is negative, then this will be here, and if C2 is negative, then this will be here, right. So, it means that when C2 is equal to 0, then depending on C1, whether C1 is positive, then it will represent this line, and if C1 is negative, this will represent this line. And similarly, when C1 is equal to 0, then it will be along your vector V1 and V2, and C1 C2 positive will give you this line and C2 negative will give you this line. Now, so it means that for any C1 greater than 0, the solution 5 represent a path consisting of half of the line u2x equal to u1y. So, this line is equation is given by xy equal to say u1 and u2. So, we can write down this line as u2x minus u1y, and the slope is given by u2 by u1. So, this line has a slope given by u2 upon u1 here, right. Now, for any C1 gets less than 0, the solution 5 represent a path consisting of the other half, like other half of this thing. Now, here one thing we may note down that lambda 1 is negative. So, it means that as lambda 1 is negative, that lambda 1 is negative. So, as t tending to infinity, your the xy is tending to 0 along the line given by this u2x and u1y. So, it means that as t tending to infinity and C2 is 0, then your solution will tend to 0 comma 0 here along the line this with slope u2 upon u1, right. So, it means that your solution will come to here. Now, similarly, we can say that solution will tend to 0 comma 0 if C1 is negative, and as t tending to infinity, solution will tend to origin through on this line itself. So, we simply say, so both of these half line paths approach 0 comma 0 as t tending to infinity. Now, we already know that y by x is equal to u2 upon u1. So, these two paths enter 0 comma 0 with the slope u2 comma u1 here. So, it means that as t tending to infinity, your solution will enter origin 0 comma 0 as t tending to infinity with the slope u2 by u1 here. Now, the other in a same manner we can say that this is your line, right. So, here also your solution will enter to origin with the slope v2 upon v1 in a same way. So, if C2 is positive, then it will come through this line, if C2 is negative, then it will come through this line, right. So, it means that solution will enter 0 comma 0 with along a particular line with the given slope, right. Now, let us assume that, so it means that the solution 5 and 6 provide us the 4 half line path which all approach and enter as t tending to infinity, t tending to plus infinity. Now, let us assume that none of the constants C1 and C2 are 0. So, it means that if C1 and C2 are non-zero, then the general solution 4 represent non-rectilinear path, means your x is written as C1 u1 e to power lambda 1 t plus C2 v1 e to power lambda 2 t, and y is written as C1 u2 e to power lambda 1 t plus C2 v2 e to power lambda 2 t. So, again, since lambda 1 is less than lambda 2 is less than 0, all of these paths approach 0 comma 0 as t tending to infinity, but not along the given half line paths. So, let us find out whether it will enter enter to origin 0 comma 0 along some line or not. So, for that you just find out the slope y by x here. So, y expression is given, x expression is given. So, you simply find out the ratio of y by x, and ratio of y by x is given by C1 u2 e to power lambda 1 t plus C2 v2 e to power lambda 2 t divided by C1 u1 e to power lambda 1 t plus C2 v1 e to power lambda 2 t. Now, since lambda 1 is less than lambda 2, so let us divide by e to power lambda 2 t. So, when you divide by e to power lambda 2 t, you will get this C1 u2 plus C2 e to power lambda 1 minus lambda 2 t plus v2, and C1 u1 divided by C2 is e to power lambda 1 minus lambda 2 t plus v1. Now, as t tending to infinity, this quantity is non-negative. So, this term will tend to 0, this term will tend to 0. So, limit of t tending to infinity y of x is given by v2 by v1 here. Now, what is v2 and v1? Basically, it is a eigenvector corresponding to the eigenvalue lambda 2 here. So, here let me look at here yeah, this v1 and v2 is the eigenvector corresponding to lambda 2. So, here we simply say that you look at this line. So, this is the line corresponding to lambda 1 and the eigenvector u1 and u2. So, slope is given by slope is u2 upon u1, tan inverse of u2 by u1, and similarly this is the line which is having slope v2 upon v1. So, it is the having the slope v2 upon v1 and it is passing through v1 comma v2, right. So, we already know this thing. Now, now it is saying that if we take any path and consider the path t tending to infinity, then this represent that your solution will tend to 0 comma 0, approach to 0 comma 0 along the line this, right, along the line this, and since it has a definite slope. So, we say that your every solution will enter 0 comma 0 with limiting slope v2 comma v1. So, it means that if we consider a solution which is starting from this, then ultimately as t tending to infinity it will try to come towards and come to 0 comma 0 and towards the line having slope v2 comma v1. So, if we have some point here, it will try to come to something like this, and similarly here if we have any path and it will try to tend to 0 comma 0 along this line, along these half lines. So, if we have a point starting from this, it will try to have say tend to origin along the line this, right. So, if we consider the next situation, this is the eigenvector corresponding to lambda 1 and this is the eigenvector corresponding to lambda 2, and since lambda 2 is bigger than lambda 1, then solution will tend to origin along the eigenvector corresponding to lambda 2. So, it means that this is the eigenvector, this is the line corresponding to the eigenvector v 1 comma v 2 here. Is it okay? So, it means that in this case your origin 0 comma 0 is a stable node, because all the solution is tending to 0 comma 0, in fact entering to 0 comma 0 along a line. It means having a limiting slope v 2 comma v 1 here. So, we can say that origin 0 comma 0 is node, in fact it is stable node, or we can say since it is entering 0 comma 0, so it is asymptotically stable node. So, in this case when lambda 1 and lambda 2 both are real, unequal and negative, then solution will tend to 0 comma 0 and enter 0 comma 0. So, in this case origin is asymptotically stable node. So, thus in summary we can say that thus all the paths, both rectilinear and non-rectilinear, rectilinear means along the straight lines and non-rectilinear means along the curves, enter 0 comma 0 as t tending to plus infinity, and all except the two rectilinear ones defined by 4 and enter with slope v 2 divided by v 1. According to the definition, the critical point 0 comma 0 is a node, and clearly it is asymptotically stable node here. So, this is the statement theorem 1, and let us consider one example based on this. So, draw the phase portrait for the linear system y 1 dash equal to minus 3 y 1 plus y 2, y 2 dash equal to y 1 minus 3 y 2, and here we can identify that 0 comma 0 is the critical point, and then now look at the determinant of the linear part, that is minus 3 1 1 minus 3, and you can see that determinant is coming out to be non-zero. So, since determinant is non-zero, so we can say that 0 0 is the only critical point. Now, let us look at the eigenvalue corresponding to this linear matrix. So, matrix is minus 3 minus lambda 1 1 minus 3 minus lambda, and we can find out the eigenvectors eigenvalues as lambda 1 equal to minus 2 and lambda 2 equal to minus 4. So, both are unequal and real and negative. So, it means that we can apply the previous theorem, and we can say that the critical point 0 comma 0 is node and it is asymptotically stable. So, it means that solution will tend to 0 comma 0 along a slope corresponding to this lambda 1 minus lambda 1 equal to minus 2. So, here I can write it lambda 2 is less than lambda 1 is less than 0 here. So, here we need to find out that it will, so corresponding to lambda 1 if it is the eigenvector. So, eigenvector corresponding to this means v1 u1 and u2. So, it is passing through u1 and u2. So, it means that your solution will ultimately enter to 0 along this line. Is it okay? So, the phase portrait will be like this, and the critical point 0 comma 0 is a node and which is asymptotically stable node. Now, this is the phase portrait we can draw here. So, let us say we have lambda 1 equal to minus 2, lambda 2 equal to minus 4, and let us say that lambda 1 corresponding to lambda 1 we have u1 and u2 as the eigenvector, and corresponding to lambda 2 we have v1 comma v2 as an eigenvector. So, let us first find out u1 and u2. Let us say that u1 and u2 here, you can find out u1 and u2. So, this is the line which represent line segment which represent the eigenvector corresponding to lambda 2 equal to minus 2. So, it means that now line segment you simply extend which contain u1 and u2, and this will represent the half lines having the slope u2 comma u1, and similarly we can have v1 and v2. Let us say v1 and v2 is here. I am just giving a pictorial representation. You can actually find out the values of u1 and u2 and you can draw it here. So, here you suppose you are v1 and v2 is here. So, this will represent the eigenvector, and if you extend these line segment here, then it will represent the line segment having the slope V2 comma V1 here, right, and along this also your solution will tend to 0 comma 0 here. So, here the slope of this is V2 upon V1 and slope here is U2 upon U1, right, and these are the line segment, and since this is corresponding to your lambda 1. So, your solution will ultimately tend to 0 along this line. Okay. So, somewhere we have a solution and it will tend to 0 comma 0 along the line this, is it okay. So, here we have a the origin is asymptotically stable node. Now, consider next theorem, theorem 2. Here the roots lambda 1 and lambda 2 of the characteristic equation 3 are real, unequal and of the opposite sign. Now, one more thing which I have missed here in the previous lecture, that here what happen if lambda 1 and lambda 2 both are negative, both are real, unequal but positive. So, in that case the only difference is your sign will be reversed, because in that case 0 comma 0 is a repulsive point. It means that all the solution will tend to infinity, say going away from origin 0 comma 0. So, in that case your 0 comma 0 will be node, but in this case it is unstable node. So, this is the case corresponding to lambda 1 less than lambda 2 and it is greater than 0. So, in this case your node origin will remain the node, but in this case it is unstable and the phase portrait will look like exactly almost exactly the same. The only thing is that now solution will move to towards the infinity along the say other sign. So, it means that it is moving away along the line, say having the slope u2 upon u1 and it will go towards infinity along the other line corresponding to lambda 2 equal to the bigger one. So, corresponding to say lambda 2 here. So, it means that it will tend to infinity along this line, is it okay. So, let me write it here. So, corresponding to this we have this line. So, this is corresponding to lambda 1 and we have your u1 comma u2 on this line and slope of this line is u2 upon u1 and this is corresponding to lambda 2 and slope is v2 upon v1 and v1 and v2 are 2 points lying on this, and now all solutions are moving away from origin and now it will, so this lambda 2 is bigger than lambda 1. So, as t tending to infinity the component corresponding to lambda 2 is bigger. So, it means that all the solution will tend go to infinity along this line, is it okay. So, here your origin 0 comma 0 is node but unstable node, right. Now, move on to theorem 2. So, the roots lambda 1 and lambda 2 of the characteristic equation 3 are real, unequal and of the opposite sign. So, in the previous case it was of the same sign, and then this case critical point 0 comma 0 of the linear system is a saddle point. So, it means that if eigenvalues are opposite in sign, then we call origin a critical point as a saddle point. So, in the same way we recall the general solution as x equal to c1 u1 e to power lambda 1 t plus c2 v1 e to power lambda 2 t, y as c1 u2 e to power lambda 1 t plus c2 v2 e to power lambda 1 t. And the particular solution in the case when c2 is equal to 0, we call x equal to c1 u1 e to power lambda 1 t, y equal to c1 u2 e to power lambda 1 t, and similarly in the case corresponding to c1 equal to 0. So, in this case we can simply write it that you have lambda 1 and lambda 2. Since these are unequal, so it means that we have say u eigen vector and v eigen vector. So, u and v are linearly independent eigenvector, right, and let us say this u is given by u1 u2 and v is given by v1 and v2, and the line, this is the line corresponding to u1 comma u2 which contain this vector u1 comma u2 and slope is u2 comma u1, and this line is passing through the point v1 comma v2 with the slope v2 comma v1 here, and depending on the C1 and C2 it will be this thing. Now here we are assuming that lambda 1 is less than 0 and lambda 2 is greater than 0. So it means that if you look at the component x here, which is corresponding to C2 equal to 0. So since lambda 1 is less than 0, your x will tend to 0, right. So it means that x is tending to 0, but y is tending to say infinity, sorry, x and y tend to 0 along the line C2 greater than C2 equal to 0. So it means that here solution will tend to origin as t tending to infinity. Now as lambda 2 is greater than 0, so in this case when C1 is equal to 0, your x and y both are tending to infinity. So it means that it will move away along the line passing through V1 comma V2 here, is it okay. So it means that for any C1 positive, the solution 5 again represent a path consisting of half of the line u2x equal to u1y, while for any C1 greater less than 0, they again represent the path consisting of the other half of this line. Okay. So also since lambda 1 is less than 0, both of these half line path approach and enter 0 comma 0 as t tending to infinity. So as we have pointed out here, the solution will enter to 0 comma 0 as t tending to infinity depending on the behavior of C1, whether it is C1 is positive or C1 is negative here. Now for any C2 greater than 0, the solution 6 represent a path consisting of half of the line V2x equal to V1y, that is this line here. This line is V2x equal to V1y, and for any C2 less than 0, the path which they represent consists of the other half of this line. But in this case, since lambda 2 is greater than 0, both of these half lines path now approach and enter 0 comma 0 as t tending to minus infinity, right. So in this case it will enter 0 comma 0 as t tending to minus infinity. So it means that as t tending to infinity, they are moving away from origin. So we are putting like this. So once again, if C1 and C2 both are non-negative, then general solution 3 represent non-rectilinear paths, but since lambda 1 is less than 0 is less than lambda 2, none of these paths can approach 0 comma 0 as t tending to plus infinity or t tending to minus infinity, and none of them pass through 0 comma 0 for any t naught such that t naught is lying between minus infinity to infinity, right. As t tending to infinity, we see that each of these non-rectilinear paths become asymptotic to one of the line paths defined by 5. As t tending to minus infinity, each of them becomes asymptotic to one of the paths defined by 5 here. So it means that if you look at here, we have path line like this. So it is solution are tending to origin along this line and moving away from this. So if I take if you take any point here, solution is starting from this, then it will try to come to origin along this line, but as it is near to origin, then it will tend away from 0 0 along this line, right. So it is coming along the line this which is tending towards origin 0 comma 0, and as it is near little bit origin near to 0 comma 0, it will move away from 0 comma 0 along the other line, right. So in a similar way, if we have this thing, then it will behave like this, and here it is like this, here it is like this. So none of the path, none of the solution is tending towards 0 comma 0 here. So thus there are two half line paths which approach and enter 0 comma 0 as t tending to infinity. These are half line paths. So one half line path tending to origin and other half line paths are moving away from origin, right. All others paths are non-rectilinear paths which do not approach 0 comma 0 as t tending to plus infinity or as t tending to minus infinity, but which become asymptotic to one of or another of the 4 half line paths as t tending to plus infinity and t tending to minus infinity. So according to the definition, the critical point 0 comma 0 is a saddle point, and saddle point is always a unstable point. So in this case 0 comma 0, the case is what? when lambda 1 and lambda 2 are not equal and having opposite sign, that is lambda 1 lambda 2 is equal to is less than 0. So, when product is less than 0 and lambda 1 and lambda 2 are real and unequal, then in this case 0 comma 0 is a saddle point and unstable point. So, now let us consider one example based on this. Draw the phase portrait for the linear system y1 dash equal to y1 and y2 dash equal to minus y2. So, we can see that 0 comma 0 is the only critical point, and we can check that the determinant is minus 1. So, we can simply check. Now, the characteristic equation of the given differential equation is given by lambda 1 this equation, and which gives the roots lambda 1 equal to 1 and lambda 2 equal to minus 1. So, both are real, both are real, unequal and having opposite sign. So, in this case your the critical point 0 comma 0 is saddle point and it is unstable here, and the graph or the phase portrait, let us say that this is the eigenvector corresponding. So, this is the eigenvector corresponding to say lambda 1 equal to say minus 1, and this is the lambda 2 equal to lambda 1 equal to plus 1. So, corresponding to this we have a eigenvector say u1 and u2. So, let us say this is the point u1 comma u2, or we can say the line passing through u1 comma u2 with the slope u2 comma u1 here. Similarly, this is the line passing through origin 0 comma 0 and passing through v1 comma v2, and the slope is v2 comma v1 here, right. Now, so here since lambda 1 is negative, so solution will tend to origin as t tending to infinity, and since this is corresponding to positive eigenvalues, so it means the solution will move away from origin as t tending to plus infinity, or we can say that solution will tend to 0 as t tending to minus infinity. Okay. So, now these are the 4 rectilinear paths, and for non-rectilinear path, if you take any solution, then it will tend towards origin along this line, and as it is near to origin, then it will move away from origin along the other line here. So, your phase portrait will be like this. Something like this. So, this is the phase portrait of saddle point, and so here in so here we will stop. So, in this case we have considered case corresponding to that eigenvalues are real, unequal. One case it is of equal sign, and in other case it is of opposite sign, and here we have seen that a case in which they are of the same sign, then origin is node and stable or unstable depending on the sign of the eigenvalue. But in other case, when lambda 1 and lambda 2 are unequal, real and are opposite sign, the saddle point 0 comma 0 is a saddle point. So, here we will stop and we will continue in next lecture. Thank you very much for listening. Thank you.